Hello everyone. Today we are discussing variational autoencoders, and in short we can call them as VAE. To start this variational autoencoders, we have to learn some basic concepts in order to fully understand its working. So we will go step by step for this process. So it will be a lecture series that will consist of multiple lectures which will be all interlinked, and once all these lectures will be finished, you will have a complete understanding of variational autoencoders. So I have divided the lecture series in following parts. So in the very first part we will review the different type of autoencoders, some of which we have already discussed, and what is the difference between the already existing autoencoders and this variational autoencoder. So we will see it in terms of diagrammatical view. Second, we will cover some basics of probability. I will not go in too much detail into the probability course, but I will discuss the only concepts which are required in order to understand variational autoencoders. In third, we will discuss KL divergence and its significance. As you will come to know later that KL divergence is one of the important concepts that has to be discussed. So I will go in details into this KL divergence derivation, and we will see what actually it is and what role it will play in variational autoencoders. And in the last, what we will do is we will derive the loss function for the variational autoencoders, which is very important. By seeing the loss function of variational autoencoders, you will feel that it is very difficult to understand, but we will break down the loss into very simplified steps so that once you go through all this lecture series, you will be able to completely understand the loss function and the role it plays for the variational autoencoders. And the last step will be coding the variational autoencoder in Google Colab and understand what it will generate and how to quantify our results. So let's start reviewing the existing autoencoders. So the very first autoencoder that we are discussing over here is basically used for image reconstruction. So by saying image reconstruction means whatever input you will give at the input node of this stacked autoencoder, it will generate the same result at the output. So in order to do that, what you will do is you will feed this feature vector of inputs into this autoencoder, which is consisting of these blocks. Here the first block is the encoder module and the second block is the bottleneck, and this bottleneck basically consists of the compressed version of this encoder module, and then the third one is the decoder module, which will decompress the encoded code over here into the image dimension, that is here. And once you obtain the image over here, what you will do is you will compare this x hat with the original image, that is x, and you compute the difference between them and calculate the loss for it. So and that loss we have to minimize, and the cost function for this image reconstruction based autoencoder is given over here. What it says is that the cost function depends on theta and phi, where theta and phi are basically the parameters that define the encoder and decoder. As you can see here, you have this theta and phi. So this theta and phi are basically the weights and the biases of this encoder and decoder module. Normally this encoder and decoder will be implemented in terms of the neural networks, and all the neural networks will consist of weights and biases. So this theta and phi defines that. And what this statement is saying is you are summing up all the features from I equal to 1 to n, and you are taking the difference between the original image minus the reconstructed image. So this is the reconstructed image. Why it is called as reconstructed image? Because xi goes through g5 first, which is the encoder, and then it goes through a function f theta, which is the decoder. So this mathematical representation represents the data flow from input to the output node, and we are calculating the difference between the two and summing and averaging it for the various samples. So this is basically the cost function that is for the image reconstruction problem. So this we have already discussed in our earlier lectures. So this is one type of autoencoders that are used for image reconstruction. Please note that I have taken this image from Lilian Weg's GitHub profile. So if you want to look into this image, you can go to her website and see from there. In the next application of this autoencoder is the denoising autoencoder. We have discussed about this in detail in DL_16 lectures. So this actually represents the typical flow of the problem. Here this represents the original image. These are the partially destroyed samples which we obtained by adding the noise from this image to this image, and the process of obtaining this from this original image is represented like this. where xi is basically the masking operation that has been done onto the original image in order to obtain the noisy version of the original image. So what we do is now we will feed x tilde into the, so this is x tilde. So we are feeding the x tilde into the stacked autoencoder, which is the same as we have discussed earlier, but the only difference is that we are adding noise at the input, and then we will reconstruct back the image, which is then subtracted from the original image, and the loss will be calculated. And this loss is basically defined like this. Please note that here this is not xi, but this is x tilde I, and this x tilde I is this one, because x tilde is obtained by adding noise to x hat. One thing I have to mention over here, that someone can ask like what is the importance of doing image reconstruction over here. Here we can see clearly that what we are obtaining is the denoised version of the original image. But what we are obtaining over here, what's the point of doing image reconstruction? What benefits we are getting from here? Are there any benefits? Yes, there is a benefit of doing image reconstruction over here. Though you can say that whatever image is presented at the input, the same is replicated at the output, but this type of network do present some advantage, and the advantage is lying over here. This Z is the compressed version of the original image, so it will represent the original image by very small number of feature vectors. For example, if the image is of size 784, and let us say that the number of neurons that are present in this bottleneck is 8, so what we are doing is we are compressing a 784 image into 8 number of nodes. So it is a compressed version of the 784 nodes. So this compressed version, if we are able to reconstruct back to the original image, means that we can transmit this compressed version onto the transmitting channel, and we can reduce the cost of bandwidth, which in turn will ultimately reduce the cost of telecommunication services. This is something similar to that of the compression algorithm, where we compress the original image from 784 to 8 pixels. So next we will discuss variational autoencoders. We can call them as VAE in short. So this is the main autoencoder that we have to discuss in this lecture series. So in order to understand this variational autoencoder, we have to go through some basic concept. The reason why I am saying this is by observing the loss function. As you can see that loss function looks very complex, and by complex I mean to say that it involves expectation operator also, it involves probability, it involves some conditional probability version also, and it involves DKL. DKL is basically KL divergence. So it involves multiple concepts in order to understand this loss function. So that's why I told you in the very beginning that we have to go through multiple lectures in order to fully understand the loss function for this variational autoencoders. I want to point out that what is the difference between this autoencoder and the one which we have discussed in the earlier cases. Let us focus on the things that are not changed. The very first thing that is not changed over here is this one, and this one. So they are same, but the only thing that is changed now is this and this. So instead of saying this as encoder, we are saying it as probabilistic encoder, and it is represented by Q phi of Z given X. And instead of saying this as the decoder, we are saying it as probabilistic decoder, and it is represented by P theta of X given Z. So we will understand all these terms when we will dig more into the details, but for now I am trying to show you what are the differences. And the second difference that I am seeing over here is that you are actually dividing the feature size, that is the X, into two parts. One is the mean and another one is the standard deviation, and then you are joining them together to form a latent vector. So all these concepts will be clear once we go into the details, but what I am trying to show you here is the differences between the earlier autoencoders and this one. So this is the cost function for this particular autoencoder. As told that it involves multiple mathematical concepts, so let's discuss all these concepts one by one, and then we will finally be able to understand this loss function, which is our target. So let's start. As you can see in the loss function, the very first thing that everybody wants to understand is the probability, because without that you cannot understand anything in this loss function. So the very first prerequisite for understanding variational autoencoders is probability theory, and I will not go into too much detail. I will just recap the simple definitions of the probability theory so that you can brush up with your probability concepts. So the very first thing that we have to discuss is the probability itself. Then we will discuss discuss the conditional probability, then the expectation, and then we will understand the KL divergence once we are confident with these three terms. So as discussed, the very first thing is the probability of a random variable x, which we defined as p of x, and it basically is nothing but it defines the probability of a random variable x, and it is denoted by p of capital X. So there is nothing great about this terminology, but the only thing is you should know that what is this p of x. So this is the probability of a random variable x. The second thing is important, that is the conditional probability. So this is conditional probability, and it is read as p x given y. So it defines the probability of a random variable x provided y has happened. So this concept is very important, and we will discuss this in terms of some numerical examples as we move further. So but for now you understand that this is a conditional, but for now you should know that this is a conditional probability. This conditional probability can also be written in terms of p y given x as p x given y, p y divided by p x. So this comes from the theorem of Bayes. You can go through the probability book and you can see how it is derived. I will not be deriving here, but this is the Bayes theorem, where p of y is basically the prior probability. So this is the prior information that is available of the system, and the ratio of p x given y divided by p of x is basically defined as the likelihood ratio, and this is basically defined as the posterior probability. So you should be aware with these terminologies. So that is why I am defining these terminologies over here. And also this p y given x can be represented in terms of the joint distribution of p x and y divided by p x. So these relations must be kept in mind because they will be used when we will be deriving the loss function for the variational autoencoders. The next concept is the theorem of total probability. What this says is, if we have y1, y2 and yn be a set of mutually exclusive events. By saying mutually exclusive events means that there is no overlap between the two events. That is, if you have one set as y1 and if you have one set of y2, so these y1 and y2 is the mutually exclusive sets. But if you have a overlap between these y1 and y2, that is over here, then it will not be defined as the mutually exclusive events because you have overlap available. So this is important, like the sets that we are considering over here should be mutually exclusive. And then the event x, which is the union of these mutually exclusive events, can be written in this way. This definition is important because we will be using it in our derivation for the loss function, so you have to keep this in mind. And this is given by probability of x given yi times probability of yi, where I runs for all the events y1, y2 till yn. If you want to observe this in terms of graphical representation, you can see over here that y1, y2 and till y4 are all mutually exclusive events, and you can observe that there is no overlap in between them. They are all mutually exclusive, and as the definition of x says that it is the union of all these mutually exclusive events. So now you can see this green line, and this is basically a union of all these mutually exclusive events. Then p of x can be written in terms of these shaded lines which I have shaded over here, and these shaded lines are nothing but the joint probability of x with yi, and we will sum it for I equal running from 1 to 4 because we are discussing only 4 events, that are y1, y2 till y4. And we know that the joint distribution can be represented in terms of conditional distributions like this, that is p of x given yi times p of yi, and this comes from the relation that we have discussed over here. So whatever definitions I have discussed over here will be used in the derivation of the loss functions. So I will suggest you to look into these definitions in detail, and if you are in doubt, you can consult any probability book also to get further confidence on these definitions. So this is basically the by substituting 2 in 1, that is, if we substitute this into 1, that is on the lower side of it, then what we will obtain is, so by substituting 2 in here, what we will obtain is this. So it's basically probability of y given x is probability of x given y times p of y divided by, earlier it was p of x, so p of x we have already said that can be written in this form, so it's basically just the substitution. So the next concept that we will discuss is the expectation of the random variable, which is defined as e of x. So the expected value of a random variable is a weighted average of the possible values of x that it can take, where each value is being weighted according to the probability of that event, and it is defined as this, that is, e of x is the weighted sum of p of x given xi times xi. Sometimes it can also be represented as x, and by defining it like this, we are saying that x has the probability density function given as p. So this is another way of representing this same thing, and the reason why I am introducing this type of terminology is because we will be using this nomenclature in our future lectures. So in order to complete this lecture on probability basics, I just want to discuss some very simple examples so that you will get comfortable with all these terminologies such as P of X given Y, and expectation of X. So let's start. So the very first example says that when a die is tossed 1, what is the probability of getting 3? So sample space is defined as basically set of all possible outcomes of this experiment. So all possible outcomes of a die being thrown are given over here. So we have 6 possible outcomes of a die. So the probability of getting a 3 is basically 1 divided by total number of outcomes, that is 6. So the probability of 3 is 1 by 6. So in this way you will calculate the probability of any random variable. So this is the second example, and in this what we have is, in tossing a fair die, what is the probability that 3 has occurred conditioned on the toss being odd. So this is important. So what we want is a conditional probability, and what we have to obtain is the probability of 3 conditioned on Y being odd. So this is important. So since we are given that the odd numbers has occurred, as the question says that the toss being odd, so the sample space basically, which was earlier 1, 2, 3, 4, 5 and 6, will be reduced to 1, 3 and 5, because now we are focusing on the toss being odd samples. So our sample space is reduced from 6 samples to 3 samples. So the probability of getting a 3 is basically now being 1 divided by 3, where 3 is the total number of samples that we have here, which is the reduced sample space from the original sample space S that is defined over here. So what you can observe, we can observe that the probability of 3 now is 1 by 3, but in the earlier case the probability of 3 was 1 by 6. So what does it show? It shows that the probability of 3 is increased when it is conditioned by Y. And what was the condition on Y? The Y should be odd. So this means it is very important to know that P of X and P of X given Y can have different interpretations. So this is basically the concept of conditional probability, where the probability of X can be affected by Y a lot, as you can see over here, where the probability of 3 in this case is 1 by 3, which is increased as compared to the earlier case, which was 1 by 6. The next example is about the expectations. Let X represents the outcome of a fair die, then what is the expectation of this X? So as we discussed that the sample space of this fair die is 1, 2, 3, 4, 5 and 6, and we also discussed that the probability of obtaining each of this outcome is 1 by 6. Then the expectation of X will be I running from 1 to 6, X times probability of X, and that can be obtained as 1 into 1 by 6, 2 into 1 by 6, 3 into 1 by 6, 4, 5 and 6 into 1 by 6, that is equal to 3.5. So this is basically the average expectation of the random variable X. So in this way you calculate the expectation of any random variable. So now we have discussed the concepts of probability theory that are required to understand variational autoencoders, and I agree that the way I carried out this lecture for probability theory is very fast, but the thing is this is not a probability course, and our main focus is to understand the loss function of variational autoencoders. So in order to make the whole lecture complete without any gap, so my intention was to introduce you to some of the basic concepts of probability. In case if still you feel confused about these terminologies, I suggest you to look into the probability books and get yourself comfortable, so that once you are comfortable then only you move forward. Otherwise it will be difficult for you to grasp the concepts that we will be discussing in the later class. So in the next class we will be discussing KL divergence, and then we will move further. Thanks for watching my lecture. See you next time.